Okay, in this video, we're going to talk about the planetary model of the atom and kind of get a couple more steps into this idea of our atomic structure. So, planetary model of the atom is probably the model that you have most learned about in middle school and previous science classes. The model was developed by a guy named Niels Bohr in the early 1900s. He actually worked under Thomson and Rutherford as a graduate student at one point in his career. Of course, the planetary model, the basic idea behind that, electrons follow orbits around the nucleus like planets around the sun. So we're seeing electrons actually as an orbit, a nice repeating pattern over and over and over again around the nucleus. And we think the electron basically rides on this kind of pattern, throughout time. Okay, like I said before, probably what you've been taught before. So what we want to do is take a look at this model and bring it from what maybe you talked about in previous science classes to more what we really believe this model shows us in our world today. So to do that, we want to talk about, first of all, middle school. In the middle school model, we use the word shells. Okay, so there's the different shells the electrons kind of sat on, the first shell, second shell, third shell, fourth shell, and that kind of stuff. And you had 2 electrons in the first shell, and then you had 8 electrons in the next shell, and so forth and so on. Okay, not a bad way to approach it, but please kind of remove the word shells from your vocabulary because there really isn't any shells out there. It's not like a Russian dolls that stack on top of each other. So no shells. A better way to explain this is that electrons work on set energy levels. Okay, so the shells we really should think about being a set amount of energy or a certain quanta of energy to them. Okay. Now, electrons always fill from the lowest energy level to the highest energy level, and we see that the first electron should fill in the first energy level, second, third, fourth energy levels, and so forth. Okay, we say that electrons only exist at certain amounts of energy. Okay, so in the planetary model, this is not something exclusive to the quantum model. The planetary model does have this idea of quantum of energy, or a very discrete, specific amount of energy to them. Very much like orbits around planets, that's thus the term the planetary model, the electrons could be at this amount of energy here, or they could be at this amount of energy here, or this amount of energy, or this amount of energy. But between the two energy levels, the space between them is completely void, which means the electrons are not allowed to be in those regions. Okay, they cannot have that much energy. Okay, having discrete amounts or very set amounts of energy are called quantum. Okay, we have a quantum of energy, or a packet of energy, basically, for those atoms. Okay, that's kind of a key part of the planetary model because with these quanta of energy, that gives us reasons why there's space between them and why each electron has a certain different kind of orbit to it because it has a different amount of energy, so it have a different orbit. Okay, now we know this model is not 100% true because if you work out the physics, electrons cannot orbit along nice circular paths. If they did, comparing their speed to their mass into how an orbit works, like a planetary orbit actually works, the electron would actually collapse into the nucleus. So we know this is not right, but it's a very good visual model. It's actually one that I'll use a lot as we go throughout the school year. Now, one of the reasons we know we have these quantized energy or these quanta of energy or these different energy levels is because how these electrons exhibit light signatures. So if you energize an atom, if you give it extra energy, you call those electrons to get excited. What happens is those electrons actually jump to higher energy levels. When they jump up to a higher energy level, okay, so let's say, for example, if they jump from the second or from the first energy level to the second, or from the second to the third, and so forth, as they jump up, they absorb energy. Okay, now that absorbing energy gives them what we call an excited state. That excited state is very unstable for an electron. It doesn't want to be in an excited state. It wants to be in its ground state or its stable configuration. So what happens is, as soon as that electron jumps up, it absorbs its energy and then it falls right back down. Okay, so it goes from jumping up to falling down, and then when it falls down back to a different energy level, which gives it a very specific amount of energy that gets released. So it jumps up, gets excited, then they immediately fall back down to a lower state, releasing energy. Now, it always releases energy in these packets of light we call photons. Most of the energy gets released in the visible spectrum. Some of it does get released in the infrared or the UV, but we see these packets of light being released in the visible spectrum, which means we can see it or track it. So here are 4 different elements: argon, helium, mercury, and neon. And we see that they exhibit these bright line spectrums where you have a lot of energy being released at this particular wavelength or a certain amount, and this particular wavelength, and so forth. So because electrons have quantized energy or set amounts of energy to them at their different levels, when they fall down, they always fall down and they give off a certain color of light, which we see as these bright line spectrums. Okay? Because we see the bright line spectrums, we know that the energy isn't spread out over a long range. It's actually very specific to very specific lines or very specific wavelengths that's in there. Okay? Now, if we jump to this website, I like this little applet because if you notice, here's an electron. It's hanging out, spinning around. And if I make a jump up, I give it some energy, it can jump up to a higher energy level. If I give it some more energy, it can jump up to another higher energy level. But then if it falls, when it falls down, the distance it falls creates a very specific wavelength of light. If it falls down again, I get a different wavelength of light. If I jump up again, I absorb more energy. And if I fall down again, I get another different wavelength of light. So every time it falls, it creates a band of light that we can see and track, okay, through a spectroscope. We can jump up, and then we can fall down, and we get another band, and so forth and so on. We can jump up, and we can fall down. We can jump up, and we can fall down. Okay, now this one actually goes off the chart, so it's not part of the visible spectrum. Okay, this happens billions upon billions upon billions of times a second anytime you're giving an atom energy. Okay, think of lights inside of your house, fluorescent lighting that's inside a school or inside your house. This is what causes the light to come off of those things. Neon lighting and all those signs we see, this is the same deal. We're giving electrons extra energy, they jump up and they fall down and emit light back in color patterns that we can see. Okay? Now, that is the planetary model. We found out, though, that the planetary model really wasn't good enough. There's some things that weren't lining up, some things that weren't working. So as a result, the planetary model is now our most recent obsolete model. And we now work under what we call the quantum model. Okay? In the next video segment, we'll talk about how that quantum model begins and how that works. Thank you.